I'm really sorry if this talk may seem like the last talk, because obviously we had the same idea. So I'm going to present our research on differential private function encryption, and I'm Spencer Lunas, and it's a joint work with Frederick Armknecht and Linda Schreier. Okay, so as many of you and also the group before us, we are interested in realizing privacy-preserving analysis, and just from a really high level view, we have on the one hand various users which have all sensitive data in some form, and on the other hand we have an analyst that wants to evaluate some function on this data, and of course we also have some sort of computational process. And in the classical medical context, for example, the analyst holds all the data and can do anything, and of course this is not privacy preserving. And we know today that not only the input data is sensitive, but also the outcome can reveal too much information about the data, and we also know how to solve this by introducing differential privacy. And I think we all have heard enough about differential privacy, so I'm not going into detail here. And we also know that the input data is sensitive and that we can use cryptographic mechanism to provide input privacy. And there are a lot of solutions that are based on multi-party computation or homomorphic encryption, but we wanted to investigate another primitive that is rather new, and it's function encryption. So again, just a quick overview about function encryption. We have our data from our different users. We have an authority and we have our analyst, and the authority provides individual encryption keys. So in a multi-input context, each user gets an individual key. The user can now encrypt their data and send them to some data holder that may be the analyst, and the analyst can now request functions and gets decryption keys for associated with this function. And we believe that this setup most closely reflects the current situation, more detailed the situation of differential privacy. And our question was, how can we use it for privacy-preserving analysis? And basically, how can we encode the noise, the randomness for differential privacy? So we present a new primitive that we call noisy multi-input function encryption, or differentially private function encryption. And here in the key generation process, noise is sampled according to a distribution D that is associated with the function f, and so the analyst who decrypts the data, or who evaluates the decryption key on the ciphertext, now evaluates not to the function f of x, but f of x plus some noise that is sampled via the distribution that is associated with f. And we so this can directly be used for privacy-preserving analysis, and there are some open questions that we solved in our paper. So first, when is the noisy output correct? How can we ensure that an attacker does not learn too much information when the outputs are noisy? And of course, how can we construct schemes? So for the first question of correctness, at first, the correctness definition for MIFE is rather straightforward. So the decryption on the decryption key and the multiple ciphertext should be f of the message, so the plain text. And for noisy multi-input function encryption, since we embed a distribution in the key generation process, we also need to deal with probabilities in our correctness definition. So we say a noisy MIFE scheme is correct if the probability that our decryption algorithm evaluates to the function plus the sampled noise is the same as the probability that this noise was sampled via the given distribution. For our next question, which is basically the security definition, we again will look at the standard security definition of a multi-input function encryption scheme. So it is a classical indistinguishability game. The attacker can adaptively make any queries of messages and also decryption keys, and so he queries some messages x0 and x1 for the slots and gets the ciphertext, and he also can query functions f. And in the normal setting for multi-input function encryption, if we only have message hiding, he only can request one function, so f0 and f1 are the same. And if we have function hiding security, which was also in the last talk, the attacker can request two functions, so for each case one. And we have in function encryption a special requirement that the evaluation of the function on the messages for each case needs to be the same, and this may seem rather restrictive, but simply means that the attacker cannot distinguish between the cases simply by evaluating his decryption keys on the ciphertext. So we have on the one hand message hiding, where we only hide the message in the ciphertext, and on the other hand we have function hiding, where we also hide the function in the decryption keys. And what we basically want is only noise, some form of noise hiding, because we do not care if the analyst knows his own function, but we care if he knows the noise or not. And so a next contribution was to adapt a security definition for noisy multi-input function encryption, and it's almost the same as for multi-input function encryption, but now for the decryption key query, he cannot request two functions, but rather one function together with two noise values. And in the key generation process, the function is also associated with a distribution that outputs one of these values with 100%. So the attacker has maximal power over the noise, and the challenger then provides the decryption key that that decrypts to f of x plus the noise pattern. And if the analyst cannot distinguish between these two cases, then he has also no additional information. So again, we have our restriction that the function f evaluated on our cipher or our plain text plus the noise should be the same for both cases. And so we show that noise hiding is only is a more relaxed security definition where only part of the function is hidden, so only the noise is hidden. And this leads us to our next question: how can we construct such schemes? So we already heard one scheme, but we also present a general transformation in our paper. If we have a function hiding MIFA scheme, then we can build a secure, noisy MIFA scheme. And this is basically what we saw before. So we take the same setup, encryption and decryption algorithm, but for the key generation algorithm, the authority first samples some value over the distribution and sets our function f star as f plus the sampled value, and then requests a key from our MIFA scheme for f star. And of course, f star needs to be supported from our MIFA scheme, and we show in our paper that if s is correct, then also our noisy MIFA scheme s star is correct, and if s is a function hiding MIFA scheme, then s star is a secure, noisy MIFA scheme. And we also present two schemes in our paper. So the first one we call noisy dot. It's a noisy MIFA scheme for inner product functionality that is built from the general transformation from a function hiding MIFA scheme. And the other one is diff pipe, which is a noisy MIFA scheme also for inner product functionality that we build directly, which has only single message security. And both of the schemes are based on linear groups. We also did some implementation and have some results that are not that fast as in the presentation before, but we did counting queries evaluation on real medical data sets, and one of these data sets was the NANUS 3 data set, which has roughly 16,000 records with each 12 attributes, and so noisy dot needs around 10 minutes to evaluate and diff pipe only 6 minutes. And this shows that the relaxation of our security notion to only noise hiding provides for new and more efficient schemes. So thank you very much. Are there any questions?
Yes, do we have any questions? Please go ahead. I can use the microphone.
Yeah, so I wanted to ask about the introduction of the new primitive. So the decryption is the addition of the noise and an f of x.
So you mean
Here?
Here? Yeah.
Would it make sense, I'm just asking, like, to have so this is a very specific relation between the noise and the f of the inputs. Would a generalization make sense? Like the decryption is a generic function, or capture other function other than addition of the vector, or the fact that we add over arbitrary distribution is generic enough?
So we use differential privacy as the basic idea, and I'm not sure if I understand your question correctly.
Yeah, it was very clear. So let me repeat. So what I'm saying is, like, it just has to do with the definition of the primitive.
Okay.
Like the decryption is f of the inputs plus the noise.
Yes.
So the operation of addition is quite specific on how f of x and the noise are related in the decryption output. Would a generalization of the primitive make sense, and would it capture other schemes or constructions that are interesting? Or just staying at this level is generic now?
It's a good question, and I'm not sure what we did the addition because it's a standard mechanism for differential privacy to add some noise, but it's worth investigating more, I think.
Thank you.
Why do you think that the computational difference is there between yours and the previous talk? It's significant. They were using pairings?
No, they didn't use pairings.
I thought it was pairings. We have this, yeah? No?
No.
Okay. So what is the difference coming from?
I think the difference is because you use only a ZP addition. So we use bilinear groups and you do not use bilinear groups, and I think this is the difference.
Okay, interesting. Any other question from the audience? If not, I want to compliment all the speakers. They were perfectly on time. Very flawless session with 6 amazing speakers. So let's give them a big hand.